Hi, everybody. Can you?
Yes, we can hear you.
Okay, welcome everybody. Into my OneNote here. We'll finish up chapter 6. You should be all the way through. And just do a little bit of nomenclature and some simple reactions in chapter 7 if we get to them. And that'll be what we cover today in class. Or will be the coverage that you have here. We'll likely get into chapter 7 today. Middle of chapter 7.
Dr. Gokul, I don't
Yes.
know if it's just me, but you're going in and out. Like you keep getting louder and then getting softer.
Yeah, you're going in and out. I couldn't hear you.
Okay. Is that better? It wasn't plugged in all the way.
Yes. Yeah.
Okay, fantastic. We're going to get into chapter 7 today. Just some brief things in chapter 7, like nomenclature of alkynes and some very simple reactions, which means that we'll be in chapter 7 tomorrow. But any new information that's presented only tomorrow is not going to be on your exam tomorrow evening. Okay. All right. Let's get here. All righty. Okay, so we left off yesterday. We finished our discussion on the epoxidation reaction. Okay, and we talked about how it's important when you're doing the mechanism for epoxidation to go ahead and set up your reaction like this. So MCPBA is a specific peroxy acid that is commonly used for this kind of epoxidation reaction. Okay, but I don't want you to just know MCPBA. Those are just letters that we can memorize. I need you to understand that MCPBA is a specific peroxy acid. So if I have MCPBA there, then yes, that's the same, that can accomplish epoxidation of an alkene. If I have any peroxy acid, you should know that it does the same thing. And the only way I can vary that peroxy acid is by changing out this R group right here. Okay. So I generally write my, if you're doing flashcards for your reactions, then I would write the reagent for epoxidation as RCO3H and know that no matter how exciting or big or crazy the R group looks, it's not the part that matters for this reaction. Okay. Notice that this peroxy acid has an OO single bond, which is very fragile. And that allows us to contribute one of those oxygens to the carbons of the double bond or the original double bond. Okay. Notice that I have this pair of electrons from the pi bond reaching out for this oxygen because there is a difference in the way these oxygens are holding the electron density. And so one of these oxygens being closer to the hydrogen is a little bit more electropositive, and one of these oxygens is a little bit more electronegative. Or maybe that's not the right way to say it, because electronegativity is inherent to an atom, and two oxygens should have the the same electronegativity. A better way to say that is one of these oxygens is more electrophilic, willing to accept electrons. The other oxygen is more nucleophilic, willing to give electrons. Okay. And so with this OO single bond, the pi bond reaches out and forms a sigma bond to this oxygen. That's why this is a dashed black bond or a wedged black bond here. Okay. And that pair of electrons, then, if that oxygen is going to accept 2 electrons, he's got to give up 2 electrons because oxygen definitely adheres to the octet rule. And so he gives up these electrons, and they form a double bond between this oxygen. Can you see my cursor today? I forget about that. Can you see my cursor?
Yes.
Yeah.
Okay. This oxygen and this carbon are going to form a double bond, which would violate the octet of this carbon, but he can release his most fragile bond, which is that pi bond. That pi bond is going to belong to that oxygen right there, right, as a lone pair. But since there's something right there, that hydrogen, able to accept those electrons, that bond happens instead, because bonding is more stable than having an O minus, right? An OH is neutral. And so those electrons go to that hydrogen, which then allows this pair right here to form the other side of that oxygen bridge. Okay. So we're forming a bridge here. It's a totally different mechanism than the previous ones. But when you form a bridge, your bridge has to be on the same face, right? You can't have one leg on the ground and one leg in the air. That's not a bridge. So when you form that bridge, it's either dashed bonds for that bridge or wedged bonds for that bridge. If we opened up this oxygen bridge, then we would have anti-stereochemistry. But because we leave that, the final product is the bridge, then it is a syn addition because that oxygen is on the same face on both of those carbons. Are you with me about syn addition? You okay, guys?
Could you just repeat that one time?
Sure. I form an oxygen bridge, which means that the stereochemistry here, that oxygen has to add to the same face of both of those carbons. So I end up with a syn addition of oxygen in an epoxidation reaction. That's why I've got my 2 options. I can either form the bridge on the bottom face of this carbon of these carbons, and that would push the propyl here out, or I form the bridge on the top face, so it's poking out of the screen, which pushes the propyl away. And that's the stereochemistry associated with epoxidation. It's a syn addition. Is that okay? We good?
Yes.
Okay, great.
Would
All
that be like a 50-50?
That's right. 50-50
Okay.
mixture of 2 enantiomers. And so what is a 50-50 mixture of 2 enantiomers? What's that term that we use for that?
Racemic.
Racemic mixture. So would your product mixture here be optically active or optically inactive?
inactive.
inactive, right? And of course, you might say, well, it's not a perfect 50-50, but the assumption is that we're going to have a roughly 50-50 mixture. And so we're going to go with that, even though we know it might not be perfect.
Okay.
Okay.
All right. Thank you.
Sure. Caroline A., hello.
Hi. So just what you just asked about it being optically inactive, that's because it's a 50-50 mixture of
Of two enantiomers.
Of
So
two
on their own,
mhm.
they're optically active, right? But everything this is doing is counteracted in terms of optical activity. Everything this species right here that I'm circling
Mhm.
is doing is being undone by what this is, by the fact that this is there in equal amounts.
Okay.
Does that make sense? So
Yeah.
individually, they are optically active because they have chiral centers.
That's what I
And-
was about to say. I knew they were optically active with the chiral centers.
But I have a 50-50 mixture of two enantiomers, and so they end up canceling each other out.
Okay.
You
Okay.
with me? Now,
Yes.
if I had another chiral center that was already there,
Uh-huh.
like this, okay,
Wait.
then all of a sudden, I've got a chiral center that's the same in both of
Mhm.
those molecules. They're not enantiomers anymore.
Mhm.
They are diastereomers.
Yeah.
Which means that what's happening at this chiral center and this chiral center is being undone by this guy. But what is happening at this chiral center is constant throughout
It's-
all the molecules. So
Yeah.
this would be an optically active mixture of two diastereomers.
Okay.
You with me?
But
Yes.
Makes sense, Caroline?
Yes.
Okay. And everybody else, you with me?
Can I actually have you repeat that one more time? I think I'm almost there, but
Sure. Let me do this actually. Who's that talking to me? I'm sorry, I can't quite see.
Julia.
Julia. Hello, Julia. So if this is my product, this is my starting material, I end up with two, excuse me for just a minute, sorry. Okay, I end up with two products, right? And they are enantiomers. And so this product mixture is going to be optically inactive. Yes, you have optically active species, but you have an equal amount of two that completely counteract each other. You with me so far?
Yes.
Okay, now if I started with a species that already had an existing chiral center that's not at the reaction site, so it doesn't get hurt, it doesn't get changed at all, then that means I introduce my excuse me. I introduce my oxygen, okay, and that pushes this propyl up and out at me. Or, okay, sorry, let me finish this product, right? And I have this chiral center that's completely unaffected by the reaction. Or I could have the oxygen on the top face, which would push the propyl away from me, right? Still unaffects or does not affect this existing chiral center. So now I have a mixture of two diastereomers. I don't have the opposite configuration at every chiral center. I have some that are opposite and some that are the same. And so my product mixture now is optically active. How's that, Julia?
Yeah, that made sense. Thank you.
Sure. Andrew?
Hi, I just wanted to know, if you added a wedged methyl like you did at the bottom, would it still be like a 50-50 mixture?
There would be, it would affect that 50-50, but we're just going to treat it as if it doesn't.
Okay.
It's hard to predict, like it's not hard to predict that the this product right here would probably form more often because the bridge would go opposite the things that are right, that methyl that's poking out. But it would be hard to predict at what ratio. So for this structure, it might be 55, 45. Is that right? Is that the right math?
Yeah.
But for just a very similar structure, it might be 48, 52. So
Okay.
at the point where we can't predict that, we would say, okay, it's going to be roughly 50-50. I imagine that it's going to favor this one, but I'm not going to worry about that, Andrew. We're going to treat this as if this is a 50-50 mixture of two products.
Okay, thank you.
Okay. Good question, though. Good observation. Okay. Caroline, is that from earlier?
No,
No.
sorry.
No,
Okay.
that's
I just want to confirm to make sure I'm understanding. So this second structure we did with a wedged methyl, it's optically active because even though the stereochemistry of the S and R and then the R and S, they're canceling because those two chiral centers aren't changing. They can't cancel out, which would make it optically active.
this one chiral center is the same, right? So whatever optical rotation that this is doing,
Uh-huh.
it's still doing that in this structure as well. So there's nothing to equally cancel that out.
We cancel it out. Okay. Thank you.
Yeah. Okay. Piper, hello.
Hey, Dr. Gokul. If you were doing a hydrohalogenation reaction and you created 4 products, would it still be optically inactive,
If you
or
created 2 sets of enantiomers, then yes,
okay?
right? But if you already had an existing chiral center that you couldn't do anything about with your reaction, and you create more chiral centers, you're creating diastereomers, and those are going to be optically active.
Okay, so you would just treat it as like, here's one set of the enantiomers and here's another set.
Yeah. If there's
Okay.
anything to if you form 2 things that cancel each other out in equal amounts, then it doesn't matter that you've got other things that cancel each other out, right? As long as things
Right.
are canceled, then you're optically inactive.
Okay, thank you.
Good question, Piper. Hi. Cassandra, we got it?
Yes, thank you.
Sure. Alrighty, everybody. So epoxidation is a synaddition, and the regiochemistry, there is no regiochemistry, because if you think about it, you're adding an oxygen to both carbons, right? It's actually the same oxygen. If you add the same group, then you're not saying that one thing goes to this carbon more often than it does this carbon. So there's no regiochemistry. Okay, just like with a Br2 addition or a hydrogenation. Okay, ozonolysis. You guys might like this one. I think you'll like ozonolysis because there's no mechanism that you have to worry about. She does present what is known about the mechanism in the book. Just don't worry about it, okay? Ozonolysis is a oxidative cleavage. So it actually is going to break your pi and sigma bond of your alkene, okay? She shows you 2 reductive workups. So ozone is what takes your alkene and cuts it, okay? So sometimes to help myself remember what ozonolysis does, I say ozonolysis slices. Ozonolysis slices. Okay, because to predict the products of this type of reaction, all you got to do is cut that double bond. You cut it and you pull it apart and you make 2 compounds. So if I start with, say, this alkene right here, right? I'm going to predict the products. This isn't how the mechanism actually works. Okay, it's just to help you get the right answer. You've got ozone. Okay, and what this step does is it cuts this double bond in half. So take that double bond, don't break the pi bond. I said cut that double bond in half, slice it in half, and put one side over here and one side over here. Oh, yeah, and one side over here. Okay, so even though it's probably I could have drawn it longer if I was really cutting it in half. But the point is you preserve the double bond, separate it, and then ozone can bring you what? Oxygens. So you get an oxygen here and you get an oxygen here. Okay, That's the ozone part of this. That's what it does, is it cuts the double bond in half and shoves an oxygen there at the end of that pi bond, okay? What the second step does is decide whether hydrogens on the pi bond are affected or not. So notice that I have 2 hydrogens here. Okay. And I have a hydrogen on this carbon as well. And they're still there. Okay. A reductive workup leaves the hydrogens alone. It leaves them alone. Those would be my products with a reductive workup. And that is like dimethyl sulfide, or she also teaches you in the textbook a zinc and acid workup. Both of those are reductive. It leaves hydrogens on the double bond alone. If you have an oxidative workup, which is not in your book, but I think that we can get there, it's going to attach an oxygen to those hydrogens, okay? But hydrogen can only make one bond. And so that oxygen is going to insert itself between the carbonyl carbon and the hydrogen, okay? So for an oxidative workup of that same, let me do this. Okay. For an oxidative workup of that same species, O3 negative 78 degrees, and then we do an oxidative workup, you still cut the double bond in half and shove in some oxygens, okay? But now every hydrogen that is on the carbonyl carbon, which was on the carbon of the double bond to begin with, gets an oxygen inserted between it and that carbonyl. So this would be this, and this would have an OH there. Now the carbon is unaffected. So if it's a carbon on that pi bond, then you don't have to worry about it. You can't break that carbon-carbon bond, but you can break this carbon-hydrogen bond and shove in an oxygen there with an oxidative workup. Are you with me? Does that make sense? The difference, if you have hydrogens on your double bond alkene, then the workup's going to matter. Okay. Hi, Piper. Piper? Oh, Kristen. Mustafa.
Oh, hey, sorry. I accidentally put my hand down when I meant to unmute myself.
That's okay. That's okay.
How do we know if it's going to be just the oxygens, like essentially splitting that double bond, or if there's going to be OH groups instead of the hydrogen groups?
The workup is what changes that. So notice here, Piper. Is this Piper? I'm sorry.
No, this is Kristen. Sorry.
Kristen. Sorry, Kristen. Notice that ozone is what puts the O's at the end of the double bond.
Okay.
And then the workup, if it's reductive, you leave the hydrogens on that double bond alone. If it is oxidative, you shove in an oxygen there on each.
Okay.
You with me?
Yeah, that makes sense. I guess I didn't notice the difference in the number 2 thing.
Well, it's a little sloppy on my part. I'm going to go down here and do it. For what it's worth, I see where maybe like you didn't notice that that's the difference, but that's what we're saying right here. The difference in workup is only significant when there are hydrogens present on the double bonded carbons.
Okay. All right.
Yeah.
Thank you.
Mm-hmm. Mustafa?
Hey, for the oxidative workup, the oxygens are coming from hydrogen peroxide, right?
That's right.
Okay.
That's right. And you know that you have a ton of reagent, right? So it like don't count like, oh, you need 3 oxygens, but H2O2 only has 1. Actually, each H2O2 is only giving us 1 oxygen, even though there are 2 there. Because after you give me that 1 oxygen, you make water. So it's kind of analogous in this way to what a peroxy acid does to an alkene, right? It gives me that 1 oxygen because that OO bond is very fragile. But then notice I make a carboxylic acid as a result, which is much more stable than a peroxy acid. So hydrogen peroxide gives 1 oxygen, and forms water, which is much more stable than hydrogen peroxide. So that's why it does it. That make sense?
That makes sense. Thanks.
Hi, Colleen.
Hey, would we need to know for the test like how to reverse if you're given like the 2 oxygen double bonds, like reverse it into the reactant?
Yeah, I mean, I can give you any 2 parts of a reaction, and you should be able to give me the rest of it, right? The third part. So if I start you with an alkene and the reagent, you should be able to predict the products. But if I give you the product and the reagents, you should be able to tell me what alkene what that alkene looked like to begin with.
Okay, thank you.
She does a really good job with ozonolysis about giving you some challenging ones, but once you get it, you just kind of lock in. You
Okay,
number
yeah.
the best way to do it is to number the carbons, like arbitrarily, but make it so that you can keep track of it. And remember that anything with a carbonyl used to be attached to each other as a double bond.
Yeah, because I did the practice problems at the end of the textbook, and those ones were a little bit more difficult because it turned into like a cyclic.
Yeah, there is one in there that's pretty challenging. If you'd like to work through it in office hours today, I welcome you to join.
Okay, perfect. Thank you.
Sure. Okay. Diego.
Hey, Dr. Google, a quick question. So, in the book, when they showed the stereochemistry, they did it a lot in perspective formulas and like Fisher projections. But are we only gonna need to know the skeletal, or are we gonna need to know
We typically
those two?
yeah, you're typically going to see reactions in the skeletal form. She did that to highlight the stereochemistry because when you have chiral centers, the easiest way to assign RNS is to have it in a Fisher, right? Like Fisher's made for chiral centers. But
Yeah.
we should be able to show the answers as skeletal structures. And here you don't form any chiral centers, so you don't have to worry about it.
Yeah, I was just asking for like the reactions. So should we only worry about the skeletal ones?
I mean, Diego, we've been tested over chiral centers with Fisher projections and with skeletal. So I can ask for either and I expect you to be able to translate between them pretty easily.
All right.
With me?
Yeah.
Okay. All right, everybody. So if I take this alkene here, which is a tri-substituted alkene, this example right here, it's a tri-substituted alkene, right? Which means there is a hydrogen on one of those carbons of that double bond, and that means that the workup's going to matter. Okay, if I have a reductive workup, I still am going to take that double bond, cut it in half, okay, and separate those 2 products, and put an oxygen right here and an oxygen right here. Okay, that's what ozone does. Ozone did that. Now, what the bottom part, the second step does is decide whether hydrogens on the carbon of the double bond is going to be affected or not, further oxidized. In this case, since it's a reductive workup, it leaves the hydrogen here alone and I make an aldehyde. I don't have to draw that hydrogen in, everyone. That's still an aldehyde. But I'm going to put it in just for us to see that that is left alone. Okay, it was already there and it was left alone. When you have an oxidative workup, you're still going to have ozone do the same thing. But if you have any hydrogens on your carbonyl carbon, they're going to get an oxygen shoved in between that carbonyl and that hydrogen. So I make a carboxylic acid and a ketone in when I when I treat this tri-substituted alkene with ozone followed by an oxidative workup, I end up with an aldehyde and a ketone when I treat this tri-substituted alkene with ozone followed by a reductive workup. You with me?
Yes.
Okay. When I have a tetrasubstituted alkene, the workups don't make a difference because I end up with no hydrogens on my carbonyl carbon, and so there's nothing to take advantage of whether I have an oxidative or a reductive workup. All right, so notice this is a cycle, which means if you cut that double bond and pull it apart, you're still attached on the other end. So if you ozonize a chain double bond, a chain alkene, you end up with two separate products. If you ozonolize a cyclic alkene, you're going to end up with one product with two carbonyls on either end. Okay, so this is, notice I've arbitrarily numbered all of these carbons just to make sure I can keep track of them. And I know that carbon 2 and carbon 8 are part of a pi bond, an alkene, so I'm going to break that. I'm going to slice that double bond in half. Okay, if you want to draw it like this, you can. You don't have to be, doesn't have to be pretty, it just has to be very clear. Okay, so I'm going to slice that double bond in half, and I'm going to leave every other bond alone, sigma bonds. The only bond I break is the pi and sigma bond of the alkene, right? And I slice it in half and leave everything else alone. So that means that here's carbon 1, here's carbon 2. 2 is still bonded to 3, which is bonded to, that's to 3, which is bonded to 4. Okay, which is bonded to 6, which has this methyl on a wedge coming out of it, right? And that's bonded to 7, and 7 is bonded back to 8. So I've got here carbon 2, there's 3, there's 4, there's 6, which is bonded to 5. There's my 7, there's my 8. 8's still bonded to 9, 10, and 11. 9, 10, 11, okay? And I put an oxygen on either end there. Since I don't have any hydrogens on my carbonyl carbons, I don't have to worry about the workup. It doesn't matter which workup I've given you, it's not gonna change your product. With me, some people like to draw it like that. Some people might wanna draw it as a straight chain out with, carbon 1 on the left there, if you will, carbon 11 all the way on the right. Either way, to me, that's clear.
So this is for anything in a ring only because it's still connected?
That's right. I'm going to
Okay.
make one product, right? So this is only one structure, one species. I still broke the carbon-carbon double bond. I still cut it in half. But
they're
the
still
rest of the molecule is
interconnected.
still intact, so we don't break any other bonds because ozone can only take advantage of carbon-carbon double bonds.
Okay, thank you.
Mm-hmm. Is that okay, everybody? Okay. All right. Now, I've used a cycle for all of my examples so far because it's the easiest one to show the stereochemistry very clearly, okay? But if you have a alkene that you start with, and it's already stereospecific. So notice what I've drawn here for you is E, 3-methyl-2-hexene. Okay, there's also Z, 3-methyl-2-hexene. Totally different starting material. If I start with this E, then there's a specific orientation of the groups, right? The methyls are on the same face, if you will, and then the propyl and, I'm talking about these methyls right here are on the same face, and then this propyl 1, 2, 3, and this hydrogen that I haven't drawn in because it's a skeletal are on the same face. And if I'm going to start with a stereospecific double bond, I have to preserve that stereochemistry while also introducing new stereochemistry that's associated with the reaction that I'm doing. Colleen, is that from earlier? Hi, Carter, what's up?
Hey, Dr. Gokul. Just a quick question. Do you still plan on releasing the bonus assignment on Gradescope?
Yeah, it'll open up around, I think I have it set for 1 o'clock today.
Okay, thank you.
Mm-hmm. All right. If I have existing stereochemistry on my alkene, I've got to preserve it while also introducing the new stereochemistry, okay? So I'm giving you, this is a strategy. Now, the strategy she shows you in the book is to memorize the terms erythro and threo. And I don't think that that is very helpful because you don't know what threos and erythros are. I mean, you might if you've taken biology and you've learned your carbohydrates, you've memorized it, but you're basically having to memorize something in order to get the right answer. So I'm showing you a different way to approach it. If you like what she shows you in the book and you get the right answer, fine. If you like what I show you and you get the right answer, fine. And if you can do both, great. Okay? I'm just giving you a different way to approach to preserve existing stereochemistry while introducing new stereochemistry. Okay? So what I want you to think about is you're looking at this alkene as if, so imagine like I'm in the midst of a jumping jack. So you're staring straight at me and my arms and my legs are all in the same plane. With me, like I look like an X essentially. So what we're looking at right now is we're looking at this double bond and it is trigonal planar. So all of this is flat, right? These are the little arms, the methyls are the little arms, and then I've got a propyl and a hydrogen legs, right? And I want you to take that alkene and lay it down on its back or on its belly. If we lay it down on its back, the methyls are going away from us, right? And the legs, propyl and hydrogen, are coming out at us. If we lay it down on its belly, then the arms, the methyls, are coming out at us, and the propyl and the hydrogen are going away. Are you with me? Are you with me on that visual? Somebody tell me. Yeah? Okay. You don't do this in any other case. We don't put wedges and dashes on sp2 hybridized carbons because they're not wedged or dashed. They're trigonal planar. But this is the way, this is the strategy for getting the right answer here. So if I laid this alkene down on its back, then the arms, or sorry, this one's on its belly, right? So the little hydrogen arms, or excuse me, the methyl arms are coming out at us, and then the propyl and the hydrogen are going away from us, okay? Or I could have laid it on its back and put the methyls away from us and put the propyl and the hydrogen out at me, okay? And then I introduce the syn addition of the oxygen to form the epoxide. Since it's syn, that means same face, so that's gonna be both wedges on the top here, or excuse me, both lines on the top here, both bonds to that oxygen, or I could form it at the bottom here. These wedges and dashes that I've created on this, they don't change. You're not altering. The introduction of the oxygen does not alter the wedge and dash that you had originally. It just moves them out of the way. So notice if the oxygen is coming in from here. So if you've got the oxygen trying to do a reaction from this face, right, at the top here, and I'm trying to interact with these carbons right here, then this methyl just needs to scoot out of the way. And if the methyl scoots out of the way, so does the hydrogen. So you just fold them down a little bit, okay? The methyls are on a wedge to begin with, in my perspective, and I leave them on the wedge. I just move them out of the way, okay? And you create two enantiomers here. You create the SS and the RR. When you form two chiral centers, how many possible stereoisomers can you have? 2 to the 2 is 4. But because this was a stereo-specific double bond, I only end up with 2 of the 4 possible enantiomers, or 2 of the 4 possible stereoisomers. Okay, Jera?
Okay, I thought I was following and now I feel completely lost. So is this for any kind of reaction with an alkene
Yes.
that has existing
So
stereochemistry?
preserve the initial stereochemistry, and then whatever this guy is, right? If it's syn addition, then both of those line bonds are going to be on this top face or the bottom face, right?
They have to match.
Have to match. If it was anti-addition, then the way I do it is, say if I was doing a BR2, for instance, right? I still do the wedges and dashes on my starting material, and then I put one BR up and one BR down, and then move the things out of the way appropriately.
Okay, it's the other things that I think are getting me lost, like the propyl group of how it's like suddenly like sticking up. It's like how it's changing directions. It looks like that's what's moving, and
It's
I
not
think
changing directions because I've left it on the same shape. I just moved it out of the way, Jera. If I
so you can
left
see it.
where it is, then my oxygen is just like, if it's exactly where it is, then how is any group being affected by the fact that they're changing their orbitals to accommodate this new single bond to this oxygen? So they're just moving out of the way.
Okay.
Keep it
And
on
some
the
of
same
them,
face, right? You don't change. It was a dash before.
and it stays
It's
a
a
dash.
dash in this case and a dash in this case. I just moved it out of the way.
And that's why those H's also stay on the dash, because that was part of the original
That's right.
stereochemistry.
That's right.
Okay. I think I'm better. I think.
Okay.
Thank you.
Yeah. Colleen, is that from earlier? Okay,
Hey,
Caroline?
yeah, sorry. I didn't realize my hand was up, but
That's okay.
thank you.
Caroline A.
Hi. Wait, could you go over again why there's only, I kind of forgot what you said. It's 2 to the 2 or something
But
like
I
that.
only formed 2 of them because this double bond was stereospecific. So if I can't swap these groups and make the S and the R.
Okay.
The
Okay.
SR and the RS. What now, if I had started with Z 3-methyl-2-hexene, I would not make these products. Does that make sense? I would make the SR and the RS now. So if I
Because
do in addition to the E, I make these products. If I do in addition to the Z, I would make the other 2 stereoisomers.
okay. I think I kind of get it, but I'll just come to office hours.
Okay.
Okay, thank you.
Julia.
Okay, so I'm just a little confused on, so this happens when we're doing an epoxidation.
Well,
but-
it's in addition because it's an epoxidation, but I could apply this strategy to any reaction. Preserve the stereochemistry on your double bond by laying it on its back or its belly, and then add the thing. If it's supposed to be anti, then you'll have one line at the top and one line at the bottom on the other carbon.
Okay, so this is just for like whenever there is previously existing stereochemistry.
That's right. And on a cycle, we've been doing it, but it's just easy to preserve the stereochemistry on a cycle because those bonds are connected to each other on the other side. You don't really have to think about it too much. But on a chain, right? When you create those chiral centers, if you create specific, right, 2 of the 4 isomers, then you need to know how to make sure that you're creating the correct 2. And that's what this strategy does.
Okay, that makes sense. Thank you.
Sure. Sarah?
Hey, okay, so when you're doing this, so for a double bond, you just put like the 2 on the same side as wedges and the other 2 as dashes.
That's right. And it doesn't matter which ones you choose, because you notice that that's why I showed here, you get the same products.
Right. So is that for syn addition and anti addition, and then you just change where you add like the straight lines?
That's right. That's right.
Okay.
An
So you
anti-addition.
always,
Sorry, I didn't mean to interrupt.
oh no, you're fine. So you always put, if you have an acyclic, to get the stereochemistry, you just put 2 on the same side as wedges and 2 on the other side as dashes.
That's right. And make sure it's the right ones, right? The methyl's looking at the methyl, so they need to have the same shape.
Right. Okay, gotcha. Thank you.
So everybody, let's do an anti-addition reaction on this same alkene, right? So if I take this same alkene, and I'm just going to choose one of the versions that I'm going to keep the propyl and the hydrogen on the wedge, right? Because it is the E, so that's the methyls are looking at each other and the hydrogen and the propyl are looking at each other. Okay? And if I introduce Br2 in a not unreactive solvent, like CH2Cl2. Okay, so I'm just doing a dihalogenation. Okay, that is an it has anti-stereochemistry because the mechanism goes through a bridge that is then opened up. Okay, so what I do is I'm going to go ahead and introduce my Br in an anti-fashion. There's a Br, and there's a Br. Or BRs on the bottom on the leftmost carbon, and the BRs at the top on the topmost carbon, on the rightmost carbon. Okay, those are my two options for introducing anti-addition of BR2. And then everything else, I just pull back in from the original structure on the type of bond that it is on. So the methyl on this left carbon is a dash. I'm going to leave it there. The propyl is a wedge. 2 lines, a wedge, and a dash. I'm showing correct stereochemistry, unambiguous stereochemistry. Okay, and then on the rightmost carbon, I have the methyl on the dash, and I have my hydrogen on the wedge. If you want to draw it in, you can. If you leave it out, it's still implicitly on the wedge because you have 2 lines and a dash. Okay, and I do the same thing for this. I just leave them on there on the same bond that I always had them on, and just kind of tuck them away so that that BR has some room. The methyl's on the dash, the hydrogen's on the wedge. And if I wanted to, I could assign R and S, but notice I only make 2 products even though I have 2 chiral centers here. And so I created 2 of the 4 possible stereoisomers because I started with a stereospecific double bond. Does that help those of you like Julia and Sarah that were asking, still kind of struggling with this a little bit? Does that help more now that we did another reaction that has totally different stereochemistry?
Yeah, that helps a little more.
Good. Okay. So this is an anti-addition of 2 BRs. The strategy stays the same. You just have to put them anti now because the oxygen epoxidation was syn, we put it syn. The halogenation is anti, so we put it anti. Okay. Sarah? Okay.
So would like the context of this question essentially be like to carry out a mechanism or reaction and just preserve stereochemistry? Like, is this a specific form of a question? I guess I'm just having trouble contextualizing.
Well, if I ask you to give me the products, and you don't pay attention to the fact that this is a stereospecific double bond, you could give me the wrong enantiomers.
Okay, so.
Right?
Okay.
I made the RR and the SS from that epoxidation. But if you're not paying attention to it, you might give me the RR, the SS, the RS, and the SR.
Got you.
Might give me the wrong 2. Does that make sense? Because you're not paying attention to preserving the initial stereochemistry. You're just syn additioning your oxygen.
Okay, I think I get it.
Or also, if I asked you, so let's pretend I gave you this on the exam tomorrow. Sorry. This question right here. And I said, give me the major organic products. And someone gives me, okay, obviously I wouldn't have done this for you, right? So let me go back up here. If I give you this problem right here, and you give me this product, you generate this in ChemDraw. Okay?
Mm-hmm.
You got the regiochemistry correct, right? Which is
Yeah.
You added the right thing to the right carbons, but you're not telling me that this is only 2 of the isomers that are possible for something that has 2 chiral centers. So I would have to take off points because you're telling me that there are 4 products that form out of this, and there are only 2 specific stereoisomers.
Okay. I think yeah, I think that makes a little bit more sense. Thank you.
Yeah. This represents 4 stereoisomers, and that's not true that you would form all of those. Okay, so only partially correct.
Dr. Gokul, do you think you can release a list with all of the reactions that we should know?
Well, so the notes, when you have, like, they're set up kind of like this, so at the top of every page is the new reaction, right? So aren't the notes just a page-by-page list of the reactions that you need to know? You with me? If you just start here and you scroll through, at the top, there's the reaction, and then at the bottom is a summary so that it tells you, feel like that's what you're looking for.
Okay, thank you.
Jara, is that from earlier?
No, I had another question.
Okay, sorry.
No, you're fine. So on these, we're doing an anti and syn. So some of them are non-specific. So would those still produce 4 products because
Yes.
they don't really
Once
care
you-
whether they're matching or opposite?
That's right. So if you did an HBr addition and formed 2 chiral centers, you could draw it without any specific stereochemistry because that represents all 4 products.
So if it started like the one on the left we did for these examples where it already had a wedge or a dash, you would write the structure of the foundation of the existing wedges and dashes and then give all 4 alternatives for the thing being added.
Well, you really wouldn't even have to at that point, Jara, if you're not having to preserve existing stereochemistry and introduce new stereochemistry, if it's all 4 products, you just draw like here. Sorry, let's go back.
Yeah, I guess I just mean like in
This
the
represents
base
all 4.
structure. Mm-hmm.
So you wouldn't even have to do wedges and dashes or worry about or even think about it because if you're getting all 4, then
Mm-hmm.
you just show a representation that means all 4.
Could you scroll down, please?
Mm-hmm.
So on the one that we get on the left that we start as the reactant, you're saying that when we put the output, we wouldn't even have to put like the hydrogen on the wedge or the dash for what we
That's
started
right.
with.
If you form 2 chiral centers from HBr, then you can just show me. So let's trying to think of one that.
So like we could start with like the same thing, the wedges and dashes, and when it outputs,
Well, you're not gonna
everything
form
is
2
just.
chiral centers though with HBr, or like.
Mm-hmm.
See what I'm saying?
I guess I'm just wondering if we get that as the base and we get a non-stereo specific as the reaction, can we flatten it out without the wedges and dashes period, or do we?
Yeah.
Does that make sense of what I'm asking?
So here,
Yeah.
Jira, right? I have a symmetrical double bond, meaning that those carbons are equally substituted, so the chlorine can go on one and the hydrogen can go on the other, or vice versa,
Mm-hmm.
right? And let me get that. So I'm just going to do the regio isomers. Okay, I add the chlorine here, say, which means the hydrogen's over here, right? And I can, since it's skeletal, that's implicit. And I also end up with this possibility, the chlorine over here, since there's no carbocation bias to one carbon or the other, right?
Mm-hmm.
And now, even though I did form chiral centers, that's all I have to draw because I formed all of the stereoisomers that are possible.
Mm-hmm.
The RR, the SS, the RS, and the SR. So I don't need to show wedges and dashes because I'll just be drawing what this already represents.
I guess my question is more of like, would our reactant, if it starts with wedges and dashes and you add HCl, do we keep the wedges and dashes in our final product drawing?
Well,
or is that not a situation
double
that'll
bond
occur?
isn't going to have wedges and dashes. It's
Oh, okay.
a strategy that I'm showing you to make sure you get the right 2 isomers if your reaction is stereospecific.
Okay.
Yeah?
Yes, ma'am.
Kristen.
So for the reaction above the one that you just drew, would the 2 halogens, I'm assuming it would be the same for the halogens, always be on opposite sides, like
Yeah,
to
it's
give
an
each other more
anti-addition
room?
mechanism. The way BR2 has to add to your double bond is always a bridge that opens up, which creates anti-stereochemistry.
Okay. All right. Thanks.
Sarah K, is that from earlier?
Yeah, sorry.
It's okay. Piper?
Hi, Dr. Gokul. I'm not sure if you just answered this, but for the reaction you just did with the HCl, why are there no stereochemistry on the chlorine?
I make for the RR, I make the SS, I make the RS, and the SR. So by not showing a specific set of wedges and dashes, I'm showing all 4.
Okay, so on our exam, do we have to show the wedges or dashes, or could we just do it like that? I guess that's kind of where I'm
As long
confused.
as the answer is supposed to represent all 4, you can write it like this.
Okay.
This represents 4 stereoisomers of this thing that has 2 chiral centers. Right?
Okay. Yes.
And so since all 4 actually form when you add HCl to this alkene, then you're good.
Okay.
But if you don't form all 4 isomers, like an example, like in this case, you don't form 4 products, you form 2 products. So you have to show me the wedges and dashes to show me that you're making the right 2 products.
Okay. Got it. Thank you.
Tyler?
Hi. I was just kind of confused on when you do get 4 products and kind of where that comes from.
So I created 2 new chiral centers here. That's chiral and that's
Yeah.
chiral. Correct?
Yes.
And if you have 2 stereo centers, how many possible isomers are there to draw?
4.
4. So I have the RR, I have the SS, I have the RS, and I have the SR.
Oh, okay.
All of those are represented here, and all of those form in this reaction, so I get to show it like this.
Okay. So you just have to draw out. Do you just draw out the 2 then?
Well, these are not stereoisomers of each other. These are regioisomers. The chlorine's on a different carbon entirely. I make 2 different constitutional alkyl halides.
Right.
Right? This chlorine is bonded to a carbon that has an ethyl, a methyl, and then this 1, 2, 3, 4, 5, 6 carbon bit. This carbon is different than this carbon. Those are regioisomers, and I make both of them because neither carbon here would have been a more stable carbocation, so they both form in equal amounts.
Okay. I guess I'm just.
But then the stereochemistry that you're talking about is all over the place. I've got the RR, I've got the SS, I've got the SR, and I've got the RS. I don't just have 2 of each of these. I have all 4 stereoisomers of both of these products.
Okay.
Okay, so I can just draw it without any without any specific wedges and dashes because I'm representing all 4. And all 4 do form.
Okay.
So I have 8 products here. 8 products. Right? The RR, SS, SR, and RS of this one, and the RR, SS, SR, and RS of this one. So you see now, if we can avoid carbocations, why we want to, but you can't. When you want to add a halogen and a hydrogen, you have to go through a carbocation. But look at what it does. You end up with a bunch of different products, and if you just wanted one of those, your yield would be pretty poor. You with me?
Right. Okay. Thank you.
Piper, Tyler, is that Tyler?
Sorry.
Tyler?
Hand down.
Okay. Courtney?
Okay, so up at like the very first one that we did that yes, okay, right here. So when you draw it, that would be partially correct because we're not showing the stereo, like we're not preserving the stereo chemistry.
Yeah, you're claiming that if you give me this answer right here, you're claiming that 4 products form, 4 unique products form from this reaction when actually only 2 do. These 2, the SS and the RR.
Yes. So I think it's easier for me to start without any dashes and wedges and then add them. Is that not smart to do?
As long as you're adding them correctly. So if you do this, if you draw this and then you want to introduce the stereochemistry, right?
Yeah.
You can't just arbitrarily decide that this one's going to be the wedge and this one's going to be the dash and then this one's going to be the dash, right? Like.
So, okay. So, but sorry to interrupt. So go back to if I draw it correctly like that and I decide to make that methyl go up, like make it a
the other methyl has to go up because that's the E, right? That's what's looking
yes,
at that E. Yeah.
because
that would be okay.
So I can do it. That makes sense to me.
Okay.
Doing it that way.
That's okay.
But then I get confused doing the other one. Do I just make it dashed?
Right.
Oh.
So.
Oh.
If you are going to do this, right? So you've already drawn this product and you do this, which means that you have to come in and do this now.
Yeah.
Those 2 are looking at each other.
Then
and
that has to be
that's
dashed.
a dash, and so is the hydrogen. Well, then you also need to show me this one. where you decide that the methyls are going to be dashes. And then this is a wedge. So that's how you would handle that.
Oh, okay. Well, then I'm not confused anymore. Okay. I can do that.
Okay.
Awesome. Thank you.
Mm-hmm. Akshar?
Hey, can you show one with a Z isomer?
Okay, so if I started with the Z,
Or is it just
go
reverse?
ahead and assume that I'm going to make the SR and the RS. Okay?
Okay.
So if I started with the Z, because I still have to do, let me move this down. Okay? I still am doing a syn addition, but my original stereochemistry is different. So if I had the Z, then the methyls are actually now on opposite, right? So that's a dash, and then the hydrogen's a dash. And then this is a methyl down here with the propyl. You with me? That's the Z isomer. Is that okay?
Yes.
That's E, this one's Z. Now I'm going to introduce the same thing, an oxygen on one face or the other. You with me?
Uh-huh.
And then I move those out of the way, dash, 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 wedge, still. I leave them as they are, but I just move them out of the way. I tuck them down a little bit. Is that okay?
Uh-huh.
And then I can also put the oxygen on the bottom, which means that I have to move all of these things out of the way towards the top, kind of. But I leave them on the type of bond that they're already shown to be on. You with me? And if I did this correctly, I should have the SR and the RS now. Priority 1, oxygen. Priority 2, the carbon with the oxygen. Priority 3 is the propyl, right? Looks R is R. Priority 1 is the oxygen. Priority 2 is the carbon with the oxygen. Priority 3 is the methyl. 1 to 2 to 3 looks S is S. And then I know then that this is the SR. So I get two different products. If I do a syn addition of an oxygen on an E, I get the RR and the SS in this case. If I do a syn addition of the oxygen on a Z, I get the RS and an SR, totally different products. Does that help?
Yes.
Okay. All right, guys, that's it. So we're only through chapter 6 for tomorrow's exam. No chapter 7. Okay, but we are doing chapter 7 tomorrow in class. It won't be on your exam, but I expect you to be pay attention and stay with me. All right, Sarah.
Hey, can you go over any regiochemistry or stereochemistry for ozonolysis?
There is no regiochemistry because both carbons of the double bond end up with the same thing.
Okay.
A double bond to an oxygen. There's no stereochemistry because you don't make chiral centers.
Oh, okay. Perfect. Thank you.
Mm-hmm. Cassandra?
Hi, Dr. Gokul. I was just wondering, can you please post this to the YouTube page?
Yeah, I'll post today's lecture to the YouTube page.
Thank you. Oh, will you post the review from last night?
Yeah, I think I uploaded. Did I not? I uploaded either the lecture or yeah. It's just loading on YouTube right now, so I've got to wait for one to go until I can put up the other.
Thanks.
Okay, Christine.
Hello, Dr. Gokul. I have a question on the screen right now. So for E is a syn addition, but like for BR2, can you explain again why is it that anti-addition?
Because the way the mechanism works is that the BR attaches to both carbons as a bridge, and then that bridge gets opened up by the other BR. And when you open up a bridge, you're going to do it on the opposite face, so it's an anti-addition.
So is it kind of work?
It has nothing to do with the stereochemistry of the alkene. It has to do with how that reaction works.
Okay,
so this is a syn addition because every time you do an epoxidation, it's a syn addition. It doesn't matter that starts with the E.
Okay, so bromine is kind of like specific type for anti-addition?
It is, yes. If you add
Okay.
two bromines, it's always going to be anti. There's
Oh,
no way
okay.
to add 2 bromines to carbons of an alkene and have them syn. The mechanism just does not go syn, it goes anti.
So is that for only bromine, or is it does
There
chlorine
are
work?
other reactions that we covered that are anti-addition, like oxymercuration is an anti-addition.
Mm.
The halohydrogen, so Br2 or Cl2 with a competing nucleophile, is an anti-addition.
Oh, okay. Okay.
Yeah.
Thank you.
Mm-hmm. Akshar, did we talk earlier, or do you have another?
Oh, no, I'm good. Thank you.
Okay. Sandra, are we good?
Yeah, sorry.
Nicholas?
Hey, I was wondering, what information did you say the bonus was over today?
It's exam 3 practice, so through chapter
Okay.
6.
Gotcha.
I've got to adjust that now because I had chapter 7 stuff on there, but I thought we'd get there today, but we didn't, so I can't put it on tomorrow's exam.
Okay. And also, where's the link for the YouTube channel at?
There's, I think I posted it, so the first time I ever put anything up there, I put an announcement on ELC, so you have to go back to older announcements. Alternatively, you can also follow the link that I have on the IR NMR question from class that I created a solution video to. I put the link in the notes, and so click that and you'll go to that video, but then you can look at the playlist and find the other videos.
Okay, thank you.
Yeah, I just typed in, sorry to interrupt. If you just type in YouTube, Dr. Gokul, UGA chemistry, your profile comes up.
Right. That'll work too, Nicholas. Michaela?
Hi, I was wondering, are we gonna get an email from Dr. Hubbard about like the new Zoom
Yep.
ID and stuff?
Yep. You'll get it.
Okay, so will that just be sent out like maybe tomorrow?
I don't know. I know that he's already got the TAs to set up the rooms, and they were expected to do that by noon today. So if they still have time before he, you know what I'm saying? You're not going to get it any sooner than noon because he's given the TAs a deadline of noon
Yes.
today.
Okay, well,
Okay,
thank
but
you.
I don't know. They'll come out for sure. They just, it's one link. So I don't. If you get it today, you get it tomorrow. I don't think it should make a big difference.
Okay, thank you.
Sure. Helen?
Hi, I was just curious when the extra credit was going to be due.
I think I have it set up for 2 o'clock tomorrow.
Okay, and then also I just had a question about the stereochemistry of all this, like the last little bit you did today in class. So we're gonna have to apply that to all of the reaction mechanisms that we've learned, right?
If your alkene is stereospecific to begin with, yes.
Okay, so
if
then
it's a cycle, you really don't have to think about it too much, right? Like we did all cycles, and it was very easy to show this in an anti-addition because you just put the groups on the wedge or the dash, right? To say like both wedges or both dashes is a syn addition, one wedge and one dash is an anti-addition.
Okay, so if say you give us a reactant and then you have the arrow and everything else, is our first step going to be okay? Where are there chiral centers? And then we figure out the stereochemistry first of our reactant and then go from there. I'm just a little confused of when I need to make sure I have dashes and wedges in my product, I guess.
To form chiral centers, then you have to be aware that you might not form all 4 stereoisomers. So if you start with a stereospecific double bond and it's not in a cycle, and you introduce new stereochemistry, right, from a syn or anti-addition, not one of your carbocation ones that doesn't have any stereospecific. It just makes all of the chiral centers. So if you start with a stereospecific double bond and you introduce stereochemistry with the reaction, then you've got to be thinking about how to preserve that from the very beginning. And that's when you would apply this strategy.
And then what you mean by if there's stereochemistry in the reaction, that would just be syn or anti, right?
That's right. So anything that's not a carbocation has a very specific stereochemistry associated with it. But if you
Okay.
don't form any chiral centers, you don't have to worry about it.
Okay.
Okay.
Okay, got it. Thank you.
Mm-hmm. Cassandra.
Hi, Dr. Gokul. One last question. I mean, I'm going to do it anyways, but I was just wondering if you've decided how much the extra assignment will be worth in terms of points.
5 points.
Okay, thank you.
Yeah. Hi, Latia.
Hi, Dr. Gokul, can you hear me?
Mm-hmm.
I just have a question about DRC accommodations.
Okay. Do you want to ask with everyone here, or do you want me to put you in a breakout room?
Could we do the breakout room?